Class, we will now discuss carbon-13 NMR. And much like the hydrogen atom, it has a plus 1/2 and a minus 1/2 spin state. Carbon-13 also has those two exact same spin states. And because they had those two spin states, and because this number right here is odd, carbon can be used to generate a NMR spectrum. So we would use radio frequencies, just like we did for the proton NMR, to make these carbon-13 nuclei resonate and do a spin flip and give us a spectrum. Now, much like proton NMR, carbon NMR, you're looking for chemically distinct carbons that are in chemically distinct environments. And so every chemically distinct carbon is going to give us a NMR signal. Now, what's interesting is that the carbon-13 NMR, the frequency that is used, or the radio frequencies that's used, is going to be significantly lower than the frequency used in proton NMR. So what this does is you can put your sample into an NMR and select to do a carbon NMR or a proton NMR. And they're separate. There's never going to be any overlap. You're never going to do a carbon NMR and you'll get some proton NMR in at the same time. No, they're totally separate experiments due to the fact that we're using different frequencies in different frequencies. So that's very convenient. There's no overlapping. Now, proton NMR, let's take a look at its relative abundance. So if we have our proton right there, its relative abundance is like 99.97%. Okay. But hydrogen does have a other isotope called deuterium, and its relative abundance is really, really small. Okay? So when you have a molecule, most of the hydrogen atoms in that molecule are going to be that. But when we look at carbon, on the other hand, things are a little bit different, because this is NMR active because it has the odd number there. This is not NMR active because it has an even number. Okay? So if we look at carbon-13, or let's look at carbon-12, carbon-12's relative abundance is 98.9%. Whereas carbon-13, on the other hand, is approximately 1.1%. So when you're looking at a molecule, 98% of the carbon in that molecule is NMR inactive. Does not give us an NMR spectrum. And the reason why those carbon atoms don't give us, or the majority of the carbon atoms don't give us an NMR spectrum, is because the majority of them are an even carbon-12. Remember, in order to have an NMR active species, this number right here needs to be odd. Okay? So now there's a consequence to this. There's a very small abundance of NMR active carbon in every sample that you have. So what happens is it takes a whole lot longer to get an NMR spectrum for carbon-13. So for example, if you had a molecule and you did a proton NMR, you could have a proton NMR in like 30 seconds to a minute, really, really fast. But a carbon NMR is going to take much longer. 20 minutes to maybe 2 hours. And it just takes a lot of time due to the low abundance of NMR active atoms. So the consequence of that is if you take this molecule here and put it into a carbon NMR experiment, you're going to get a lot of noise. You see all this noise right here. So it's really difficult to say, hey, is that a peak or is that just noise? You see? So what you have to do is you have to do the experiment over and over and over and over again. So you're doing what's called a signal averaging. And when you do a signal averaging, it cleans up the noise. So now you see, hey, we got a little less noise here. And now we have signal. Now when you look at the signal here, we are always going to have a solvent peaks. That's because we have deuterated solvent. We still use the deuterated solvent, but you're going to have a carbon there, and there's going to be some carbon-13 in that solvent. There's just no way to get around that. So you will always have solvent peaks. And then you will always have your TMS peak. Okay. So this molecule right here is going to give us 3 signals. So we have 1, 2, 3. So just like proton NMR, if I ask a question, how many signals would you expect for that molecule? You would say 3. That's how many. You would not say 5. Okay? I hope that's clear. 3 signals for that molecule. Now, in most carbon-13 NMR, and I'll just say it this way, in all carbon-13 NMR that we're going to see in this class, you're only going to see singlets. They do not split. Okay? That's another interesting feature about carbon NMR. No splitting of peaks. They're only singlets. Okay? Now, what we have here is like, okay, these peaks right here represent these carbons. But we need to be able to specify and label which carbons are responsible for each signal. So what we have going for us here is these tables. These tables are going to help us out. Now, when you look at these tables, it's looking at the carbons and their chemical shifts. And one thing that you'll notice is that the chemical shifts for carbon-13 NMR are large in comparison to proton NMR. Proton NMR went from 0 all the way to like 12. But in carbon, we go all the way up to 200 and even past 200 ppms. So how we identify which carbon is responsible for these peaks right here is we have a little table that helps us out. And I want to focus your attention on this group right here. Remember what we called that when we were discussing proton NMR? That's a methyl group. All right. And what about that right there? That's called a methylene. Methylene. And where's our methine? Right there. There's our methine hydrogen. But we could also say, hey, those are a methyl carbon, a methylene carbon, and a methine carbon. I'm going to introduce a new one, and it's this guy right here. When you have a carbon attached by 4 alkyl groups, we call that a quat carbon. And you can see each different type of hydrogen, a methyl all the way to the quat carbons, they have different chemical shifts. So these chemical shifts will help us to predict our NMR. So if we look here, I see we have a methylene and a methylene and a methyl. So since there's only one methyl, if I go to the table, where would I predict that chemical shift? Around 10 to 25. Okay? So I go and look and be like, okay, 10 to 25. Well, there's a peak in that range. So that signal right there, if we label it, that carbon is represented by that signal right there. Now we have two methylenes, which are going to be those two, but which one is which? Because when you go to the table, methylenes right here says 20 to 45. Okay? And both of those are in that range, 20 to 45. So how can we distinguish between this guy? Let's label it B and C. Now, why am I labeling A, B, C? Because each of those carbons are chemically distinct. So we have three chemically distinct carbons. Now we can use the same principles that we've learned in proton NMR. We see that carbon C right here is next to a electronegative atom. So inductive effects tells us that carbon C has to be further downfield. So that would make that signal C. And then just by process of elimination, that would be signal B. So all the principles that we've learned in proton NMR can apply to carbon NMR when determining and predicting signals and where they show up. Okay, so there's that. There's another table right here that just shows you other chemical shifts of other carbons. So if you see carbons in this range, then you have a pretty good idea that you have a carbonyl compound. And carbonyl compounds are that. So if we draw ourselves let's draw ourselves an ester here. No, not an ester, a ketone. Like that. That functional group is called a ketone. The whole molecule is a ketone. But this little section right here is called a carbonyl. So we can call that carbon the carbonyl carbon. So when you're doing a NMR experiment and you see signal around that range, there's a good chance that you have carbonyl compounds or carbonyl carbon. Same right here. Okay. So things to just get familiar with and look for. Now, in carbon NMR, we do not have integration. So the peaks have no integration, and so you just have to be careful because the heights of these peaks don't tell us anything about how many carbons there are. Okay, so now that's a big point to remember. No integration for carbon-13. So let's take a look at this molecule and now let's assign the peaks. And what we're going to do is use the tables to help us out. So I can see that we have a carbonyl carbon, a methyne, a methylene, and two methyl carbons. That's what I've noticed. And so we can go back to the table and identify them one at a time. So if we call the carbonyl carbon A, I'm going to go back to the table if I've forgotten and say, hey, that was a aldehyde, right? Let's double check. That carbon right there is a aldehyde. Or sorry, this whole molecule is an aldehyde. And so we have a carbonyl carbon. So where do carbonyl carbons show up? Around there. And do we see a peak? Boom. There it is. So we can say with confidence that this carbon right here is A, and that signal right there is A. Now we have a hydrogen coming off of here, our methine hydrogen. So where would we expect that signal? We would expect it around 25 to 45. Do we see that? Well, there's a 25 to 45 range. So in here, there's a signal. So that signal right there is going to be called B. Now we have a methylene, which we will call C. And go to the table. Methylenes are right here, 20 to 45. That's in that range right there, 20 to 45. So that's going to be our C. Now we have D and E. We have two methyl groups, and we have two signals left to label. Now, which one do you think would be further downfilled? Well, it's going to be E. E is going to be further downfilled because it is closer to the oxygen atom, the electron withdrawing group. Or, sorry, the inductive effects of the oxygen atom is going to decrease or deshield the electron density for the methyl group on E. So we would say this peak right there is E, and then that one would be D. And that right there is TMS, and that is our solvent, so we don't have to worry about that. So as you see the process here of identifying the signals and to the molecule, we follow the same principles in proton NMR. Okay. Now, I want to do another example with you. Is what if we had a molecule that looked like this? Let's see here. So we have a ketone. How many signals would you expect? So I don't want you to fall for this trap that you'd be like, well, there's 1, 2, 3, 4, 5, 6, 7 carbons. So there's seven signals. Can't do that. We have to figure out how many chemically distinct carbons there are. Okay? And what I see here is that there is a plane of symmetry. So if there's a plane of symmetry, then that means A and those two carbons right there are equivalent. So that would also make B those two equivalent and C equivalent. And then this guy right here, that's our carbonyl carbon, and that is a carbon, so it will give us a signal, and we would label that D. Okay. So we would expect 4 signals. Okay. Even though there's 7 carbons, there's only 4 chemically distinct groups of carbons. Okay. So with carbon NMR, you can use the replacement test as well. Okay. So if you wanted to, you could draw out this methyl group right here, like so, and then ask yourself, are these two methyl groups equivalent? So you would just do the replacement test, and so you would take this whole methyl group right here and replace it with an X, and then you would draw yourself another molecule, okay, and then replace that one with an X. And now you will compare these two molecules here, and you will figure out by the replacement test that they are in fact equivalent. Okay? There's another carbon NMR experiment called DEPT. And the DEPT stands for this phrase right here: distortionless enhancement by polarization transfer. Fancy long name. You don't need to remember that name or what it means, other than you just need to know how to use it at this point, okay? So we have depth spectroscopy. And what's really cool about depth spectroscopy is that it can distinguish between a methyl carbon and a methylene carbon. So what we see here in this spectrum here, do you see how we have signal right here above the baseline, and we have signal below the baseline? Now compare that to this NMR. All these signals right here are above the baseline, and the baseline is right here. But in depth NMR, you have a top half and a bottom half. And if you have signal on the top half, it's going to be two types of carbons. It's going to be a methine carbon or a methyl carbon. So when we look at our molecule here, we see, hey, you have a carbon there with one hydrogen right there. There, right? All those are going to be up here. And then we have a methyl, which is going to be right there. But then we have a methylene, and that methylene is shown down there. So isn't that cool? That this really helps us to figure out our NMR if we use a depth, because now we can distinguish and find any methylene carbons. Really, really cool ability there. Okay. Another feature that you need to be aware of depth NMR is that you're only going to get signal if the carbons have hydrogens directly attached to them. If there's no hydrogens attached, then you're not going to get any signal in a depth NMR. So if you have like a ketone, the carbonyl carbon there will not show up in a depth experiment. Okay, so that is NMR, and we will be practicing these principles in class and in your homework sets. So I highly encourage you, if you have any questions, please don't hesitate to ask.